Okay, let's begin. We have some examples from last week to finish up. Convergence. Okay, so we did that problem where we had to identify and sketch the ellipse. Let's do the one where we have to this one's not so bad, problem 3. They already kind of gave you in squared form. Okay, how do we get to a point where we can sketch that? How do you sketch that?
By dividing by 21. Divide everything by 21.
Okay.
She hit the camera. Someone hit the camera walking in.
What happened?
I think she accidentally hit it walking by.
He's like, I'm sick of this. No more damn ellipses. Or maybe she was excited. Maybe she's like, yes, ellipses. I gotta get some excited. Okay. All right. Now what?
Name of the center and the other numbers.
Okay. What is it? 3 and 7 is the guys we're gonna want to use here.
Red 3 and red 7.
Right. Right. So let's just write it like that, so we don't make the mistake of actually looking at the wrong thing here. So I definitely want to think of those as being over squares. Okay. So those are both 2s. Yes, they're both 2s. So what would that look like? Picture right here. So we now know the center, which is 2, 2. Just put that there. Now what do we do?
You would move up and down
By
radical 3.
No.
Oh, sorry, rad
You
7.
move up and down
Yeah,
by rad
and
7,
left
that's
and-
under the y.
And left and
So-
right by rad 3.
Go up by radical 7, which is somewhere between 2 and 3. That'll actually bring us below the x-axis here. And we would do left and right by radical 3. Radical 3 is a little less than 2, so we don't actually get all the way to the x-axis there. What do I do with that?
Draw the box.
You create a box based on that, and so this is saying that there's like this invisible box that we're stuck in. And then your graph, which is going to be an ellipse, just touches these 4 points that you put in, and so it's going to be that's it. Let's do problem 4. I just care that you know how to actually recognize what it is and sketch it. Okay, step 1. What's the first thing to do? Identify and sketch.
So kind of group the x's and y's together.
Okay, 4y squared minus 24y minus x squared minus 2x. Just move the 31 over there.
And factor out common factors of the y's and then the x's. And then complete the squares.
What does that look like here?
So it's plus and minus 9 in y.
So you take half the coefficient of this and you square it and you add and subtract it. So plus 9 minus 9. That will be plus 1 minus 1. Now, the first 3 terms upon doing that will be a complete square. So this part here will become y minus 3 all squared. We're left with a minus 9 out here. This part will become x plus 1 all squared. We're left with a minus 1 out there. So now we'll expand that. So this is 4y minus 3 squared. 4 times 9?
36.
Minus x plus 1 squared plus 1. Now we are simply going to move these guys to the other side. So this would be minus 32 plus 36. That will give us 4. Okay, now what?
Divide everything by 4.
Divide everything by 4. So I would get y minus 3 squared minus x plus 1 squared over 4 equals 1. And what is that?
Hyperbola.
It's a hyperbola. Now, of course, the center is going to be center.
Negative 1/3.
Huh?
Negative 1/3.
Negative 1, 3. How does it open? Left or right? Up and down?
Up and down.
So it opens up, down. Okay, now let's sketch that. Okay, how do we start? What is the first thing we sketch here?
The center.
Sketch the center. Minus 1, 3, let's put that there. Now what?
Move up and down 1 and then
There's a 1 squared here,
and then left and right too.
so I move up by 1, down by 1. So this would actually bring me over to 2, that would actually bring me over to 4. And our 4 here is 2 squared, so I will move left and right 2 units. So I will move to the left, that's going to bring me all the way over here to positive 1, and move to the right, it's going to bring me all the way over here to -3. Okay, now what? Get the same box. Now what?
Try the asymptotes.
Asymptotes. So pretty much you have the diagonals and you extend them. Now,
You draw the line like going upwards and downwards, but like
yeah, where's the point it passes through here? Well, we know it opens up and down, so it's going to meet on the blue line.
yeah.
So it's going to be passing through this point. And it opens asymptotically to these guys. Opens up and down. And so the black is the graph, the black is the hyperbola. That's how you sketch that one. That's all I wanted to do really. You should really know how to sketch those. That's going to help you out in the next class. I think that's all I wanted to do here. There's some more topics here about like rotation of axes and stuff like that, but we don't care. Do that if you're interested. But I actually really want to start a whole new topic. Kind of excited about. Even though I'm not sure, I'm out of it. Groggy for something. I actually had a decent amount of sleep last night. I just didn't sleep well, I guess. Feel very groggy, but let's power through because we have some exciting stuff to talk about. Well, we have some preliminaries to the exciting stuff, but then we'll talk about the exciting stuff. We'll start the exciting stuff. The preliminaries to the exciting stuff. We are going to talk about something called a sequence. Sequences. 11.2 we get to the exciting stuff, why we would care about sequences. I mean, sequences are important in their own right, but we mostly care about them because of what they're going to help us with the future sections of chapter 11. So we're starting chapter 11. And in that first chapter, it starts talking about sequences. So let's figure out, well, what are sequences? Let's do a fuzzy definition here. Just try to be very intuitive. A sequence is a list of numbers in a definite order. I can create a list of numbers in some specified order according to some rule or formula or pattern. I call such a list a sequence. So we can have -1. I have a list here. -1, 1, 7. Dot, dot, dot. Or I can have 1, -2, 3, -4, period. Or I can have something like right? So there's a rule in my head I was thinking of when writing down each of these list of numbers. There is a definite pattern to them. The ellipses here basically mean, whenever I write that, this means pattern continues indefinitely. Usually you just imagine that it goes on forever. Here, this one, the sequence ends. And of course, the guys where the patterns kind of continue moving on forever, we call these guys infinite sequences because they kind of go on forever. Infinite sequence. Whereas this guy I would call a finite sequence. So I can have a finite list of things, I can have an infinite list of things. See the pattern here? What would the next number be? 9, and then 11. The pattern here is to add 2 every time, starting at -1. That is an example of something that will be called an arithmetic sequence. You probably see all those in high school. This one is also an arithmetic sequence, but it's alternating, but not really arithmetic. It's called an alternating sequence because the signs alternate every other one, but that also has a definite pattern. I'm just like counting up in absolute values, but I change the sign. However, I terminate this one at 4. Anyone recognize this sequence?
Yeah.
It's Fibonacci sequence, very famous sequence. People geek out about it all the time. Pretty much the rule is you start with 2 things, and every new number is the sum of the previous 2 numbers. This is kind of like a model for how a rabbit population grows. This was Fibonacci was studying at the time. So these sequences can have all sorts of applications and meanings, and we use them to judge patterns. And sometimes there's a nice formula that you can deduce that the numbers follow. Other times it should be defined for you, and because you probably don't know what's going on in the user's head. I don't remember the actual list of numbers, but I remember when I was in Calc 2, the professor wrote down a sequence of numbers like, guess the next number, and we were sure the next number had to be that. And we're like, no, it's this. And we're like, how do you get that? Well, the pattern was the numbers on the 5 train. That's like the number of street stops. Like, that's not fair! Okay, so there are times when there's a pattern and we can create a formula for finding that pattern. So that's called a sequence. Let's talk about notation. We can name sequences. Usually by lowercase letters and subscripts. In various degrees of detail. So, for example, if someone who's really pedantic, they're going to name a sequence, for example, AN, and then they're going to tell you, my n starts at 1 and goes on forever. Right? So that is the main way to name a sequence. So you can define the starting point. This is called an index. Well, n is called the index. The number here tells you the starting point, and the number up here tells you the ending point, where you write infinity if sequence is infinite. Informally, we may write just brackets and an, and whenever I write that, you'll know I'm talking about a sequence, or I'll just write an when lazy. Okay? So from now on, I write something like that, you know I'm talking about a sequence. Terms in a sequence are the particular numbers and they are named based on their position. So I can say the sequence AN from 1 to infinity is the sequence 0, 1, 1, 2, 3, 5, 8, dot, dot, dot. In which case, the 0 is what we would call a sub 1. This will be called a sub 2. This would be called a sub 3, and so on and so forth. So if I describe this sequence to you and I say, oh, look at the element A5. I'm talking about the 5th guy in the sequence. 3 in this case would be called A5. So those are called the terms of a sequence. Each of these are the terms. So I can talk about the 8th term of a sequence, the 56th term of a sequence, etc. So a sequence is just a list in a definite order. We won't really use this interpretation, but it'll probably be important for the future. Note, a perhaps better way to think of a sequence is as a function with domain is just the set of positive integers, or sometimes the non-negative integers, depending on the disposition of the author. There are people who get in a heated debate whether 0 should be a natural number or not. We shall not do any such debate. It'll be understood whenever I'm using it. So you can think of this as just some function, which we call a n, that takes the number 1 and maps it to 0. And then it takes the number 2 and maps it to 1. Then it takes number 3 and maps that to 1, takes the number 4, maps that to 2, takes the number 5, maps that to 3, takes the number 6, maps that to 5, etc. Right, so you can think of this as just a function where we're taking inputs from the set 1, 2, 3, etc., and we're just connecting them to the terms of a sequence. And a lot of times, it will be convenient to actually think of a sequence this way, and we can figure things out that way. Another thing that's important for a sequence, we say a sequence an converges to a finite number L if the limit as n approaches infinity of a n equals L. And we may write an arrow L. So there's the idea of convergence for a sequence. We can find the limit. We can look at the n. If we can figure out a formula that gives us the list, we can write a n as a formula, and then we find the limit as n approaches infinity. And we want to see, does this actually settle somewhere? And if it does, we can write this. Otherwise, the sequence diverges. So that's the idea of convergence versus divergence of a sequence. Now, in terms of how to actually go about dealing with that, all rules about limits will apply here, as well as any limit technique, you know. So you're going to have to remember all your techniques about limits that you have, L'Hopital's rule, all that good stuff. They will apply here, and there are familiar properties that you will experience here. So things like, suppose a n approaches L, b n approaches m. Then it turns out that the limit, you can find the limit as a n you find the limit of a constant times the sequence. That's just going to be a constant times the limit, which is just c times L here. So you can factor constants outside. Limits distribute across sums. So if I add two sequences together, find the limit, it's just going to be the sum of the individual limits. Which here it's going to be L plus or minus n. Limits, they will distribute across multiplication. And division. As long as you're not dividing by 0. And you can move limits inside of powers. So all of those things are still true. So if you want the limit of a n raised to some positive power k, this is just going to be the limit of a n raised to the k. So all these properties still hold. So the limits with sequences, they behave just like limits of real numbers, almost. Note, we may write, as you saw me just get into a habit here, just LIM, and when considering a limit, since, so I'm giving myself permission to be lazy here, because we will always be considering the infinite limit. So it goes without saying. It is important to realize that when we're talking about a sequence, we have discrete outputs. So there's always going to be a gap between things usually. So you can't really arbitrarily approach any other number because the limit idea just doesn't work. What you can do is you can track what the numbers are eventually approaching and as an entire group, and then we can talk about the limit that way. It's always going to be a limit as you approach infinity. It'll never be anything else. So, for example, I can talk about, so define a sequence an is given by n. I can talk about what is the limit of an. Well, what you would realize that is if you started tracking this, and if I start at n equals 1 going off to infinity, then at 1, my an is going to output 1, so it's going to be here. At 2, it's going to output 2. At 3, it's going to output 3. At 4, it's going to output 4. 5, it's going to output 5. Now, as you can see, I can't arbitrarily approach n equals 2 because there's a gap here, right? It doesn't make any sense to actually do that in terms of how limits work. However, I can start to see that these points are on some sort of trajectory. I can kind of talk about the trend that the sequence is following as a whole, and in this case, we would have infinity, because the outputs are just getting larger and larger and larger and larger, and so I can say that. So I can say diverges to infinity, for example. So it will not actually make any sense to take any other limit other than the infinite limit, because in general we just can't get close in the interim. We can only get close as what a trend is doing. So we'll always look at the infinite limit. We'll never be looking at any other limit when it comes to sequences. And that's how they differ from limits of real numbers. Another example, say my AN is a sequence defined by AN equals 1 over n. That is another example. I'll just draw a picture here as well, even though we don't really need it. So we can draw n versus AN, thinking of it as a function. So at 1, not drawn to scale obviously, put that up here. At 2, that's going to be at a half. At 3, that's going to be at a third. And so on. At 4, comes down, 5 comes down, 6 comes down, right? So again, isolated points, can't really get close to any one of them. However, I can see that there is some sort of trend that the outputs are following, and you can see that that trend is going to be that they're getting closer and closer to 0. The outputs are getting closer and closer to 0. Theorems. I should probably tell you about those. Here's one. It's going to come in handy sometimes. If the limit, it's always going to be n versus infinity, of the absolute value. So you take a sequence, you take the absolute value of all the terms. If you realize that that approaches 0, then the limit without the absolute values will also approach 0. So sometimes so for example, let's say you're considering the limit of AN where your AN is -1 to the n over n. Now that one might be kind of weird for you to consider because you will notice that this is going to consistently change signs. So if I were to graph this one out, when n equals say 1, you'll notice that this outputs -1, so it's down here. When n equals 2, it outputs positive a half. When n equals 3, it outputs negative a third. 4, positive a fourth. 5, negative a fifth, etc. So we have this thing that's jumping up and down. And it turns out, how do you actually track this thing if it's doing like this? You just realize that the signs are alternating, so you can take them out of commission. You can just be like, okay, consider the limit of the absolute values of AN. This is the limit as n approaches infinity of 1 over n, because I just take the absolute values, it kills all the signs, and that one we actually found was already 0. This means that the limit of the original is going to be 0. BTW, this works because of another theorem, which you might as well just remind you of here, the squeeze theorem. We have a squeeze theorem for these guys. So it says, if AN, BN, CN are sequences with, I always have my BN is less than or equal to AN, and that's always less than or equal to CN, and I know that BN converges to some number L, and Cn converges to some number L. Then AN must converge to L. Because I can take limits of everybody, the limit of this side goes to L, the limit of that side goes to L, so the limit of this is between L and L, it has to be L. Example here, limit limit as n approaches infinity, sine n over n. We can start by noticing that our sine of n is always going to be between 1 and minus 1. Even if we're only plugging in positive integers, that's going to be true. And so I can divide by n on both sides, on all sides. And then I can take the limit of all sides. And this one approaches 0, that one approaches 0. And so we can get that limit is 0. We can also have, there's another example. To once again illustrate something that we kind of already know. Let's say I'm taking the limit of, say, n factorial over, say, n to the n. So that's my sequence. What do you think that converges to? Zero. You should have learned in Calc 1 that this guy's always bigger than that guy. In sequences though, it's actually easier to prove. Basically, we can just note an would kind of behave this way. And factorial just means what? Do you know what this means?
Multiplying by every number below
Right.
n as well.
Right, so you would start at the number 1, you multiply all integers counting up to n, so this would be 1 times 2 times 3 times 4 times, going all the way up to n minus 1 times n. And in the bottom, we would have, well, n times itself, n times n times n times n times n times n times n. So now what you realize, if you want to take the limit of this kind of thing, you can kind of do this separation because we have integers. I can just think of these as just a bunch of multiplications here of different fractions. In which case I can use the rule that the limit would just divide across these guys. So it's the limit of 1 over n times the limit of 2 over n times the limit of 3 over n times the limit of n over n. And this would go to 0, that would go to 0, that would go to 0, and this guy goes to 1. And so I just have 0 times 1, which is 0. So that actually approaches 0. This reminds us of a nice thing. Well, one part of this list, just in case you forgot it. Logarithms are, in general, much smaller than polynomials, which are in general much smaller than exponentials, which are in general much smaller than factorials, which are in general much smaller than these were kind of exponentials as n approaches infinity. So as n approaches infinity, guys on the right are much bigger than guys on the left, to the point where guys on the left might as well be 0, might as well not even try, might as well not even get up in the morning. That's okay. Yeah, it's true. Okay. One other thing we might want to need to talk about. Increasing versus decreasing sequences. We say AN is increasing if each new term is greater than or equal to the previous term. We say AN is decreasing if each new term is actually smaller than all previous terms, the previous term. And so you can either show that a sequence is increasing or decreasing, like are the outputs getting larger or smaller as a whole, by figuring out that. Note, we can also use calculus here. So we can say AN is decreasing if the derivative with respect to n of AN is less than 0, and AN is increasing means the derivative with respect to n of AN is greater than 0. Okay, so I think that's all I wanted to tell you about sequences. We'll do some homework where you'll try your hand at some problems. But these guys I just want us to know a little bit about because of what they're going to help us with, which is the next section, 11.2. Okay, so now this is the important thing. Series. Very important mathematical tool, series. Very important in calculus, very important in many areas of mathematics. Including calculus. Let's talk about what a series is. We're going to spend a lot of time on them. The rest of the semester is going to be spent on series. A series is the sum of the terms of a sequence. That's what it is. Take a sequence, take a list of numbers in a definite order, and decide to, let's add everybody up. Notation, you know it. It's this uppercase sigma, where again, we will tell you where we want to start and where we want to end. So, we can talk about that. And again, this number here is called the index. This is the starting point. This here is the ending point. And we write infinity for infinite series. And essentially what this means, meaning, whenever we write something like 1 to infinity of an, basically means plug in 1, add it to plug in 2, add it to plug in 3, add it to, keep going. Now we have finite series. This means you actually stop the process somewhere. So 1, 2, let's say a big N of AN. This just means A1 plus A2 plus A3 plus dot, dot, dot. But you eventually stop somewhere, A sub big N. Not very interesting, very rarely applicable. Versus infinite series. These guys are the guys where they start at some point. This particular one starts at 1, and you just keep going. You keep adding forever. These are interesting. And applicable, very applicable. It turns out some infinite series does this thing that we call converge. That is, they sum to a finite number. Now, probably a year ago, you guys would have been surprised by that, but of course, that's not surprising at the moment. For example, a Riemann sum is an example of an infinite series. That sums to an integral. All of integral calculus is really you calculating infinite series. When you say the integral of sine of x is minus cosine of x, what you're saying is if I make a bunch of dissections of areas and add up an infinite number of them, if the height of the area curve is defined by sine x, then this is going to add up to a number minus cosine x. Once upon a time, this was very strange. There is something called Zeno's paradoxes, where this guy came up with a bunch of paradoxes for some things that in math today, it's really not paradoxes at all. One famous paradox is the Aero Paradox. Basically, you imagine someone shooting an arrow at a target, and the idea is, well, what if you theoretically think about how the arrow covers the distance between the person who's shooting and the target? Well, you can think of it as it always covers, there's a point in time where you can stop a stopwatch and say, okay, the arrow has made it halfway to the target. And then you can stop the stopwatch again when it has covered half of the remaining distance, and then half of that distance, and then half of that distance. And so you can kind of, let's add up all the distances that this arrow has traveled. Well, it will start at a half. So half of, let's say you have a really powerful arrow and it's like a mile away, right? There's a point where the arrow would have traveled a half a mile. And then there's another point where it will travel a quarter of a mile. Then there's a point where it will travel an eighth of a mile. Then there's a point where it will travel, a 16th of a mile, and so on and so forth. Always covering half of the remaining distance. And so you might say, if I were to add all these fractions, would they add up to something? And the answer is yes. They would, of course, add up to 1. Right? Which is kind of strange when you think about it, but then you realize that when someone shoots an arrow at a target, it actually does make it to the target. So because you theoretically come up with this idea of splitting up distances, doesn't change the fact that the arrow will eventually hit the target. I can add up an infinite number of things and get to a finite answer, which we've been doing every time we get an integral. We just didn't realize we were doing it because we are hiding behind formulas. So this idea is going to be very important. It is important for us to know when the series will converge. When, how, I'll talk about the how. might get to talk about that in this class. When, how, and possibly to what an infinite series converges. And this will be the subject of the next 2 or 3 classes or so. Us figuring out when would a series of infinite terms actually add up to a finite number. How do I know they're going to add up to a finite number? Can I figure out what that number is going to be? And then we'll spend a couple classes on actually using applications and doing some applications of that. So if a series sums to a finite number, let's call it S for sum, we write sum of a n goes from 1 to infinity equals S. And what it means is the following. This means, because of course you can't just write down a bunch of infinite additions on a page and expect anyone to know what that really means. What does it mean to add up an infinite number of things? Here's how we will define it. This means the sequence, so this is pretty much the whole reason why I told you about sequences in the first place. The sequence of partial sums converges. That is let me tell you what a partial sum is. So, definition. A partial sum, Sn, that notation kind of means I'm going to think of it as a sequence, is a sum of the first n terms of a series. Let's do an example. Consider this series. Let's do the one I just mentioned. N equals 1 to infinity of 1 over 2 to the n. So that's a possible series that I can consider. You will notice that that is just adding up 1 over 2 to an integer power. So this is going to be 1 over 2 plus 1 over 4 plus 1 over 8 plus going on forever. Then the partial sums are, I can talk about S1. This is called the first partial sum. This is just the sum of the first term, 1/2. Then I can talk about S2, the second partial sum. This is going to be 1/2 plus 1/4. I can talk about S3, the third partial sum. I can talk about S4, the fourth partial sum. And etc. And I can talk about, in general, the nth partial sum. It's 1 over 2 plus 1 over 4 plus 1 over 8 plus ... 1 over 2 to the n. I want you to notice we defined a sequence here. I can pretty much use a sequence to track these outputs. So there's a list of numbers that I now care about. This creates a sequence of partial sums. Sn. And if Sn converges to some number S, we write the series equals S, and we take that to be the sum of the series. And you can see that this idea works in the finite case very well. You can do this with a finite number, and that is going to actually work. So we kind of think, we just define this to work in the infinite case as well. I can figure out what an infinite list is going to add up to if I just add a finite number of terms at a time and see, is there a pattern that I can take advantage of? And if there is such a pattern, we can actually talk about the infinite series converging, FYI. The above sequence Sn can be described, I'm not going to show you how we get it, but I'm just going to tell you, it can be described as the following. You'd realize you're able to do this and actually compute all those answers here. This guy is going to be 2 to the 1 minus 1 over 2 to the 1. If you add those up, you'll actually get 2 to the 2 minus 1 over 2 to the 2. Add these up, you'll get 2 to the 3 minus 1 over 2 to the 3, and etc. You'll realize that this is a pattern you'll be able to find. And if you take the limit of this guy, the answer is actually going to be 1. Because as n goes to infinity, the minus 1 is not going to matter. The 2 to the n's will control everything, and so we have a ratio of 2 to the n's, and we get the answer is actually 1. So I'd be able to say that the sum from n goes from 1 to infinity of 1 over 2 to the n is 1. It'll all add up to 1. Now I'm going to talk about how you would know that pretty soon, well, in future classes. But for now, just take my word on it that that's what it's going to add up to. I want to get a lot of definitions out of the way so that we can start doing the interesting stuff starting next class. Let's talk about some important definitions. Definition. We say the series AN converges absolutely. Absolutely it converges, Tom. If I put absolute values around each term, it will still converge. We say a series converges absolutely when this property holds. Now, it might seem like those two things will always happen at the same time, but they actually don't. There are things that if I put absolute values around each term, it doesn't converge, but if I take the absolute values away, it will converge. So for example, if your AN has a bunch of pluses and minuses in it, sometimes it's growing, but you have a bunch of things subtracting from it, so it kind of decreases the growth and slows the growth down enough so that the infinite number of terms will actually add up to a number. But once you put in absolute values, now there's nothing stopping the growth, and so it will actually diverge. So there's something that's called absolute convergence. And this just means if I put absolute values around the terms, it will converge. There's another definition. If you realize that the series converges, but the series with absolute values does not converge, we say the series converges conditionally. So when I mentioned earlier about how something converges, this is mostly what I was talking about. Something can converge absolutely, or it can converge conditionally. Here's a mind-blowing fact. There's something called the rearrangement theorem. Has anyone ever heard of this thing? Rearrangement theorem? No, does not know. So, Riemann, the same guy who came up with Riemann sums, which is why you guys are all suffering through calculus now, in his paper, probably his first paper, he probably wrote that for his PhD thesis, I don't remember. The same paper that he defined the Riemann sum in, this new way to think about integration, which was 100 and something pages. On one of the pages of this thesis, there was this thing here called the rearrangement theorem, which he kind of mentioned in passing, which is a completely crazy fact, which kind of shows you the kind of weird behaviors that an infinite sum can have. It says the following. If a series AN converges conditionally, and R is any real number, then there exists an arrangement of the terms of AN such that the sum will be R. I want you to think about that for a second. This is something that does not happen in the finite case, right? If I'm adding a finite number of numbers, it does not matter in what order I add them. I can arrange them in whatever way I choose. They'll always add up to the same thing. If I'm adding 1 and 2 and 3, it doesn't matter if I did 1 plus 2 plus 3 or 2 plus 3 plus 1 or 3 plus 2 plus 1, it doesn't matter. I will always get the answer 6. When you're adding up an infinite number of terms, this is no longer true. I can have a series that converges conditionally. That's the whole thing. Conditionally means I can actually rearrange the terms to cause it to add up to any number I choose, any number I want under the sun. If something conditionally converges, I can say, you know what, I want it to add up to pi, and you'll be able to rearrange the terms so that it adds up to pi. I want it to add up to e squared over 3. You'll be able to rearrange the terms so that it adds up to e squared over 3. A conditionally convergent sum, its convergence is very tenuous. It doesn't actually stay the same upon rearrangement. And in fact, an arrangement also exists. As I say, arrangements also exist. That will cause the sum to add to plus infinity or minus infinity. So you can actually take a conditionally convergent sum, you can arrange the terms so that it diverges. With absolutely convergent series, this is not the case. If AN converges absolutely, to S, then all rearrangements will converge to S. So in the future, there'll be times where I'll ask you about, does the series converge? Does it converge absolutely? And it's not just to torture you, it's because it's really important for us to know if the thing I'm looking at converges absolutely or it converges conditionally, because a lot of math is not going to work with something that only converges conditionally. For example, integration wouldn't work, and calculus wouldn't really work the way it works. If I can talk about the area under a curve, but if I swap these two rectangles, now the area changes, it's not a very useful technique. Like, it depends on how you're arranging the rectangles. The answer is going to change on me. You don't want that to happen, and it turns out to not have that happen, you need absolute convergence. So with absolute convergence, it is the gold standards of convergence. It tells us it will converge in a way that you can manipulate the series order, which you might have to do for some reason, and it's not going to actually change anything. If something is conditionally convergent, though, you change the order, you now change what it adds up to, potentially. So that's really important. So later on, we're going to be doing calculus, where I'm going to tell you how to integrate and differentiate series, and certain properties that I do, it's going to depend on them being absolutely convergent. We'll stop there. Still have a few more definitions to get to, but we'll get to the fun stuff shortly after with the next class. We'll stop there. See you later.